the chair or moderator for this morning's session, and I will be doing a brief introduction to each speaker and then handing the floor over to them in terms of sharing their presentation. A reminder, please, to post any questions that you may have in the Q&A session, and after each presentation we will have an opportunity just for brief clarifications with regards to the presentation. But after each of the three presenters, we have a 15-minute session where we'll then deal with all of the questions that have been posed in the Q&A, online Q&A box. So please do post your questions as we go through the presentations this morning. Also a reminder, and I think it has been shared in the chat box, after the presentations, we encourage you please to vote for your favorite presentation. The link has been provided in the chat box where you can do that, and please, I encourage you to vote for your favorite presentation of the session this morning. As I said, we have 2 slots, each of 45 minutes, so we're together for 90 minutes, and it certainly looks to be an engaging and insightful session that we have this morning. So first of all, a big thank you to, we have six speakers this morning, and I just want to check, I think I have control of the presentations at the moment. There we go. It should be online and we should all be able to see that. If there are any problems, please also do let us know with just posting a comment in the chat box. So with that, I'd like to hand the session over to our first presenter of this morning. Eleanor Lebry is joining us from the University of Queensland in Australia. The title of her presentation is Decarbonisation to Drive Dramatic Increase in Mining Waste, Options for Reduction. So Eleanor, I'm going to pass it over to you, and hopefully you have control of the presentation to move through. Thank you.
Thank you, Linda. So let's see if I can control what's happening on the screen. Like it? Okay. So these are my slides. So hi, everyone. It's a pleasure to present at this conference today. Today, I'm going to present a paper that has been published earlier this year in Resources Conservation and Recycling. And yeah, so just to quickly get into the topic, I'll start with something that you probably all know, which is that the global commitments to decarbonization are going to require an initial big amount of metals to be mined. And so the first focus of my presentation today is on mining and mining waste. So essentially, we can expect more mining and therefore more mining waste. Just to note that I'm not accounting for the reduction in fossil fuel extraction. That's of course, on this side, there should be a decline. I'm really focusing my presentation on metals and metal waste. So, and specifically the types of waste that I'm looking at, if you look at the diagram here, is two specific types of waste, which is waste rock, which is the product of the mining stage, and tailings, which are the product of the mineral stage. I'm not looking downstream of this because mostly because the other types of waste are often generated outside the mine site. So there's a bit of a delay in my slide control for some reason. There, okay. Oh, now I've done too many slides. Okay, so the first part of this paper, we just looked at 4 metals and expected production outlook until 2050, and we estimated the amount of waste rock and tailings that would be produced as a result of this expected production. I'm not the person who did the calculations for this, so I might not be able to answer your questions later, but essentially we can see on the slides, so on the right, you see the amount of waste rock and tailings that would be produced, and you can see that there is a very nice exponential curve. And so that's the beginning of the paper, and then we go into the discussion of, okay, how can we reduce this amount of waste? And first of all, why do we want to reduce this amount of waste? First of all, we want to have a reduction in volume because volume of waste is basically one of the main problems that we have with mining waste. So the more volume, the bigger the land disturbance will be, and the more land is used to store waste where it could be used to do something else with it. We also want to reduce toxicity because waste can leak out of the mining boundaries and cause an environmental contamination. But this is a very common phenomenon called acid mine drainage. And what we also want to avoid tailings dam failures. And tailings are often stored in a liquid state. They are very fine particles that are very hard to store over the longer term. And sometimes tailings dam fail in a catastrophic manner. So these are the three types of reduction that we are aiming for. And so what we did in this paper is review alternative processes that have the potential to achieve reduction in waste in one of these three ways. I'll quickly go through them. I don't have a lot of time for this presentation, so happy to expand a bit later in the questions if you have specific questions about specific processes. We have reviewed 6 of them. So first one is reprocessing, where basically we take the waste that was generated by one previous operation and we reprocess it to extract more metals. That achieves reduction type 1, so reduction in volume. The second type is a waste management technique called environmental desulfurization that basically just removes the reactive component from the tailings and produces more benign tailings, so that reduction in toxicity. The third that we looked at was dry stacking and commingling. So that has the effect of essentially removing the water component of tailings, generating safer tailings. We also looked at pre-concentration and coarse particle flotation. This is an added step in the process, which generates another type of waste. So in terms of achieving volume reduction, it doesn't achieve this at all. In fact, it adds more waste, but it does reduce the quantity of fine tailings, which is the part of the waste that can be problematic from a risk of dam failure perspective. We also looked at ore sand co-production, which is a co-production that is really embedded in the mineral processing stage, and it achieves a reduction in volume, and at the same time, it produces a second product aside from the main product, which is the metal that we want to extract. And finally, in situ recovery, which is really bypassing the entire process, the entire kind of conventional mining process, to just simply extract directly in situ. So we reviewed all of these alternatives and we found that basically none of them is a miracle solution. That's not a surprise. None of them achieves all type of reduction at a reasonable cost with reasonable energy and water usage. So all of them have significant trade-offs. But what we discussed afterwards is the potential of pairing some of these approaches and the potential for concurrent implementation. So I'll just briefly talk about this as well. So pairing is, as the name suggests, is just putting 2 or more than 2 of these methods together. For example, environmental desulfurization using basically the benefits from extracting more metals, regenerating benefits from the sale of these metals and compensating for the cost of environmental desulfurization. That's one example of how mixing reprocessing with environmental desulfurization to kind of go together well. I'll just quickly provide another example. For example, having in-situ leaching, but having in-situ leaching as a reprocessing technique. So instead of putting it at the level of the ore body, you can put it at the level of the mineral processing stage, and the tailings that are produced can be leached in situ to generate more metals, but as well produce more benign tailings. So there are a few different examples of pairing that could work well. I'll also very quickly talk about concurrent implementation, which is basically implementing these different techniques in different spots all around the world, along with conventional methods. So there's no perfect solution, but depending on the location of the mine and the characteristics of the mine, some methods will be more appropriate than others. And I'll just quickly talk about this later. So basically, we had a very simple scenario for concurrent implementation, and we show that we can achieve some reduction in waste. Again, nothing miraculous. It's not that easy, but we could achieve some significant reduction in waste. And I'll just, quickly move to the conclusions. So given the amount of mining waste that we can expect to be generated under a business as usual mining scenario, we think it's critical that alternative pathways are implemented to reduce waste. Sorry, don't know why this moved. Just trying to go back.
Are you able to move back just to your important last slide? There we go.
Yes, good, okay. So I just want to insist on that second point, and then I'll be done with my presentation. I just want to say in the topic of concurrent implementation, we think that it's really about choosing where these methods and these approaches can be implemented. And for that, we need to understand the geographical, hydrological, mineralogical profile of the site itself and understand the context in which these methods can be applied. So for example, reprocessing might be a technique that is very valuable in the case of a site that has been already heavily impacted and you reprocess waste from an old legacy site, whereas in situ leaching might be an option where you're in a sensitive area and you want to have minimal disturbance as possible, while at the same time knowing that you're not going to extract as much metals. So I think that really at the end of the day, the design of this, the choice of these different techniques is site dependent. And I'll just leave it here. And yes, thank you, Linda.
Lovely. Thank you very much, Eleanor. I don't see any questions of clarification in the Q&A online box from our participants who are joining us. So I think, Eleanor, I'm going to park some of the questions that I have as well until we get to the Q&A session at the end of this first slot. So thank you for your presentation. With that, then let me see. We're going to move to our next presenter this morning, Stefan Guillaume, who's joining from Vienna University of Economics and Business in Austria. The title of the presentation is Europe is a Major Importer of Deforestation Embodied in Metal Products. Certainly a fascinating title, so I look forward to this presentation. And Stefan, I'm going to pass it over to yourself. Hopefully you've got control of these slides.
Okay,
Lovely.
Thank you, Linda, for the introduction. Let's see if I already have.
I believe that you do have control. There we go.
Yeah, seems to work. Great. So good morning, everybody. I'm Stefan Guillaume from the Vienna University of Economics. And the presentation I will give is part of the Fine Print project, which is a 5-year project funded by the European Research Council. And as you can see below, this study is conducted in cooperation between my group in Vienna and several colleagues in Australia from the University of Sydney and from the University of Queensland. So the objective of this study was basically to develop and test a method that allows us to trace deforestation caused by the expansion of mining areas and trace this deforestation impacts from the mining countries via the processing sectors all the way to the final consumers of various products. The questions we wanted to address with this study was which forest areas have actually been lost to the expansion of mining in the past 20 years and where has this loss occurred in geographical terms. Then the second question, which raw materials were mainly responsible for this land use change and the forest loss we observed. And then finally, the question related to international trade and consumption. So in which consumption the deforestation ends up, basically, which countries and sectors are responsible as a final driver of this deforestation embodied in internationally traded products. So in fine print, we started around 4 years ago to use satellite images to quantify the land use of the global mining sector, so how much area is actually appropriated by the expanding mining sector. We covered very different types of mining, as you can see here. For example, large-scale industrial mining in the Andean mountains, as well as more artisanal, small-scale mining, for example, of gold, typically happening in various parts of the Amazon. Last year, we published the second version of this data set. It's openly available, and the data set contains around 45,000 polygons of mining areas, basically all over the world, as you can see here. And these mining areas sum up to more than 100,000 square kilometers, which the mining sector directly appropriates to extract various forms of various types of metals, industrial minerals, coal, etc. Yeah, and the map here shows also the expected hotspots of mining, like in South America and the Andean mountains in the Amazon, or if you look at Southeast Asia, Indonesia, as we will see in a moment, is a clear hotspot of forest loss related to the expansion of mining and various other hotspots around the world. In order to calculate the deforestation or the forest loss due to the expansion of mining areas since 2000, we overlaid our global data set on land use with a global data set on forest change. You might probably know this Hansen 2013 data set, the first version published then. We used the data in that version up to 2019. And this has allowed us to calculate how many hectares and square kilometers of forest was actually lost as mining areas grew in the past 20 years. And the results of these calculations we first published in a study in April this year, which we published and produced together with the WWF called Extracted Forests. And here you can see, as mentioned earlier, that Indonesia turned out to be a real global hotspot of forest loss. So there were around 3,500 square kilometers of forest were directly lost due to the expansion of mining, in particular of coal, but also mining of other metal ores like nickel, bauxite, and other metals. Yeah, and Indonesia is followed by Brazil, as you can see here, a second, but also significant forests were lost in Russia, Canada, and US. In terms of commodities, we identified two main hotspots driving the deforestation on the global scale, which is gold on the one hand and coal on the other hand. If you look at the black bar here for coal, it's clear that Indonesia is by far the #1 hotspot for coal-related deforestation, but also the US, quite significant forests were lost to the expansion of coal mines, in particular in the east of the country. If you look at the gold ore bar, you see that the extraction is much more distributed across many regions globally. So we have some countries in the Amazon, but also in Southeast Asia, in Africa, etc. And deforestation related to other metals was quite significantly lower, as you can see here. So if we want to calculate now the deforestation embodied in international trade, we need to connect our data on land use and on forest loss due to the expansion of mining to a global trade model. And for that study, we selected the multi-regional input-output database Gloria, which you can see here. Gloria was developed for the International Resource Panel to calculate a variety of different consumption-based indicators. And connecting our information on forest loss to Gloria allowed us to trace the embodied deforestation in the various products that use, for example, metal ores as an input, and see which final demand drives the deforestation in countries worldwide. So now I'm stuck. No, here we are. Yeah, just selected two result slides. Here you see the top 12 consuming countries, meaning final demanding products that contain or embed deforestation related to the expansion of mining activities. So the top 12 countries consuming products aggregate to almost 80% of the global total forest loss since 2000. Yeah, you see the ranking is led by China. China contributed 80% to the global total forest loss in the last 20 years, but the EU already ranks second with 14% of the global total induced by the final consumption of either private households or government or investment in the EU. And this is followed by the US and Japan, as you can see on the slide. And we also looked at the sectors that mainly drive the inducement of deforestation in the EU, and that's basically, as can be expected, sectors such as vehicles, such as metal products, or also the construction industry. Just a second result slide on the footprint side of the story. For the EU27, it's particularly remarkable that a large fraction of the EU impact is located outside the EU borders. So 85% of the mining-related deforestation footprint of the EU27 is located in non-European countries. And here you can see some of the most important contributors like Russia, Indonesia, but also African countries like Ghana or Australia contributing to the footprint of the EU. Which leads me to my final slide, and I just pick out 2 points for discussion, which we might expand on also later in the discussion section. So on the one hand, we found that around 10,000 square kilometers of forest was lost directly due to the expansion of mining since 2000. And you might argue that this is quite a small number compared to some other drivers of deforestation like agriculture. But there are also some arguments that that support looking at mining in the future. As Eleanor has already mentioned, mining will significantly expand in the future due to various increase in demands. I would also argue that the indirect effects of mining induced in the surrounding of mines, like infrastructure development, would further increase deforestation rates. And often it's the case that drivers reinforce each other. So if you have agricultural concessions overlapping with mining concessions, it's very likely that the areas will be deforested. And just a second, more policy-oriented point, as our results show, the EU has a clear global responsibility to take action and care what's happening along global supply chains. And the upcoming EU regulation, like the Sustainability Reporting Directive, for example, will certainly increase the demand to report on those mining-related impacts, including forest loss. So we think that these type of assessments and data will also become more relevant in the context of company reporting in the future. Final slide, if you want to learn more about the Fine Print project, please visit our website. With this, back to you, Linda.
Thank you very much, Stefan. Thank you for a very interesting presentation. Again, I don't see any clarifying questions in the Q&A. For those that are joining us online, please a reminder just to pop any questions that you do have either into the chat box or into the Q&A box, and we'll work through those during the course of this morning. So Stefan, thank you very much for your presentation. And with that, let me pass over to our third speaker in slot 1 this morning, who is Gertfried Jungmeier. And Gertfried is joining us from the Uranium Research in Austria. The title of the presentation is Methodological Framework to Assess Climate Neutrality and Circularity with Dynamic LCA, the case study of e-trucks. So Over to you, Gottfried.
Yes, hello everybody. I want to address this time, everybody's talking about climate neutrality and circularity. And what I'm presenting today is what is the scientific methodology to address these two most relevant issues. And the answer is it's dynamic life cycle assessment. And I will show you the main results on very practical application on a case study we do on electric trucks. I don't know how I can move to the next slide.
You should have control of the presentation.
But I don't see any
It's not moving.
element to click. They say I can change it, but I can't see it.
If our online tech support can assist with this one, I'm not sure if it's just a page down. I don't know, Stefan and Eleanor, you have experience having gone before. Any guidance?
Yeah, for me, it just worked with enter or page down to move to the next.
Okay, I try this one.
Although I understand there is a delay between slides.
Yeah, it's not working.
Are you seeing on top of your screen orange bar that says you have control of the presentation?
I see that one.
Okay, so that's a good sign.
But where do I click?
They say you can use the arrows on the keyboard.
Okay, I will try this one. It's not working.
Otherwise, I'm happy if someone wants to pass the control to me and I'll move the slides on your behalf. Go for it.
Yeah, that would be fine.
There we go.
Yes, here we are. And the results I'm going to show to you today is a work we do together with the International Energy Agency in the Technology Collaboration Program. There's a specific activity ongoing with 10 countries globally to assess climate neutrality and circularity using dynamic life cycle assessment. Next slide, please. And the big question, of course, what is a dynamic life cycle assessment? At least life cycle assessment is a method to estimate the environmental effects over the lifetime of a product. So you always have to cover the production, the use phase, and the end of life phase. And the nice thing or the interesting thing on dynamic life cycle assessment is that everything is going over time. So you count over time the effect of the production, of the use, and the end of life. If you click twice, please. In that graph, you see on the x-axis, the time is running. And on the y-axis, you can put up the different environmental effects. And the two systems you see here, they have different emissions in the production phase, different emissions in the use phase, and of course, in different emissions in end of life phase. Relevant in life cycle assessment is on one hand, what is the cumulated effect over time? So if A is bigger than B, of course, the system B has lower environmental impacts compared to system A. Mentioning, of course, these two systems provide the same service over the same time. And if you click again, you see another system here. It's a system C, which has the most interesting way of cumulating up environmental effects. And the interesting thing is you have the production phase, which might be higher than from the other two systems. But during the operation phase, over time for a vehicle, it could be 5 to 10 or even 15 years, you see that the cumulated emissions are flattening down. So you do not at a certain point, you do not add any additional environmental effects. And that is a good thing. And even in the end of life phase, if you're able to recover secondary material, also the environmental burdens might go down because you allocate the secondary materials to being used in another product. So they disappear out of this product system and go into another product. And if you click 2 times, so the interesting thing on what we are interested is, on one hand, we know climate neutrality is a very visionary target, because to have a service without having any climate effects is really visionary. But what we see here, this green system has in principle a perspective to go towards climate neutrality, which means you do not emit any additional climate effects starting at a certain time. And secondly, if the effect in the end of life is decreasing, this is very relevant for circularity, because in that case, you also have the possibility to go toward circularity if you're able to recover most of the material again for another purpose. This is quite a perfect way towards circularity. So this is the principal methodological framework. And now I will show you how we apply this to electric trucks, comparing it to other systems. Can you go to the next slide? Here you see, this is a mistake in the picture. It's not a greenhouse gas. This is the primary energy demand you see in the graph. But anyway, it will look similar. What we do here, we are comparing different trucks using different propulsion systems. And these are only the emissions on the production phase. And that means if you have an electric truck, you have to build the truck, of course, which is the green part of the graph here. But also, if you make an electric truck, you also need additional electricity. So you have to invest in wind farm, photovoltaic, hydropower, or whatever. So you also have to build up new electricity generation system. And you see this here in the black bar. So in the production phase, you build the truck and you also build additional electricity generation. And that has to be included in the system in the operation phase. If you also go to a catenary truck, this is the blue part here, you also have to build up the catenary truck and so on. So the main idea is really to count all the emissions you need to establish the system in the very beginning when you start your life cycle assessment. And in the next graph, you see, the next slide appears now. Here it is. In the next slide, you see the same picture I've shown you on the beginning, also showing you the cumulative greenhouse gas emissions over the lifetime of the different trucks. The black truck here is the diesel truck. It has a low emission to establish, but it has very strongly increasing emissions during the operation phase. The green lines are the electric trucks. And you see the electric trucks, they have a higher emission on the very beginning because you have to build the trucks and the battery and the additional electricity production. But then during the operation phase, it's nearly a flat line. It's only just some additional maintenance you need. But that means once you have established the system, it has the possibility to go towards climate neutrality because you do not add any more greenhouse gas emissions. The blue line are the hydrogen trucks. And you see here, if you run a hydrogen trucks, you have on the beginning nearly the double emissions to establish the system and to run the system. And the red lines here are e-fuels, where you make synthetic diesel made from CO2 and renewable hydrogen made from renewable electricity. And they have the highest emissions because they are so much less efficient. You have to install so much more additional electricity to put in place. And that means when you start to operate these different trucks, it's very important how much emissions have already been spent when you start to drive the truck. Yeah, and then if it's a flat line, you see it has, all of them have the possibility to become climate neutral, except the ones using fossil energy like diesel. Of course, they have a still increasing emission. On the next slide, please, you see the same graph. On the next slide, you see the same graph, but this time also concentrating on the primary energy demand, because the minimum is always to look on greenhouse gases and on primary energy demand, because energy efficiency is quite relevant. So it's also important to see which of these systems needs how much primary energy. And you see here again in the beginning on the left-hand side, this is the energy to establish the system. But of course, all these systems need energy during operation. So all these lines are going up, and the steeper the lines are going up, the more energy you need to provide the same transportation service. But if we talk about primary energy, it's not only relevant the total primary energy, it's also a question how much of this energy is renewable and not renewable. So the right-hand side graph shows you only the renewable part of this primary energy demand. And here again, you see that the electric trucks have, I would say, 5 times less demand on renewable primary energy demand, because they are so much more efficient than the e-fuels or the hydrogen, which is in between. So energy efficiency is, of course, quite relevant also towards climate neutrality. Next slide, please. The other aspect we are trying to assess is the circularity. Yeah? So we are judging for a so-called circularity index, which means if that index is 0, you are not circular. If this index is 1, it's a total circular system. That means that all the material is reused. And this nice thing is, if you use this material circularity index and you have already made an LCA, you have all the data available from the production phase and the end of life phase to calculate this material circularity index. I can show you on the next slide. We did this for the different vehicles. I don't see the next slide at the moment.
Yeah, apologies. I seem to have lost control again.
What you see on the next slide is at least the calculation of this material circularity index. The worst case is to be linear, then you're on the left side. Circular means green on the right-hand side. And the black bar here says that a conventional vehicle roughly has 0.55 material circularity, which is at least, I would say, significantly higher compared to a battery electric system. It's a green one, it only has 0.46. The reason is that the recycling of the battery is not so well established today as it will be in future. But if you look on the dark green bar, where you are able to reuse the battery for a second life, if you put it out of the vehicle and put it in a stationary application, it's a kind of reuse. Of course, you can already increase the material circularity index. And the blue bars just show you for the different materials, they have different circularities. This was my main message, and this is just the final slide on the details of this international activity we do around the globe. We have partners from North America, from Asia, and Europe. And if you have any further questions, please ask them or contact me later. Thank you very much.
Thank you very much, Gerfried. Apologies for those tech glitches at the start of your presentation. I'm just checking to see if we have any questions in our chat box yet. Wait, I'm not sure what's happening now. Okay, I'm not sure what slide this is, but anyway. I don't see any questions in our chat box again. So in the 6 minutes that I have before we move over to our second slot for this morning, I do have some questions myself that I would like to pose to our speakers. First of all, Eleanor, to yourself, maybe Stefan, Eleanor, if you can just share your screen so that people can see you. Lovely. Eleanor, to yourself, the question that I had is obviously the most logical place to start would actually be to reduce the amount of mining waste that is actually generated when one mines. So to move towards kind of more precision mining, that you're really just taking out the ore body and not, you know, the overburden and additional waste rock that comes with it. But I assume, I mean, there's obviously a lot of technology development work around that in terms of reducing the amount of waste that's mined at the start, because that's additional cost to the mining company. But what would be the driver? Because these interventions that you're talking about, because you're suggesting they're very site specific, what would be the driver that would really force mining companies to adopt these practices to reduce mining waste post extraction? Is it legislative? Is it cost? What would be the drivers for them?
That's a very good question. As well, so I didn't have the time to mention as well in the presentation. There is also the opportunity to go underground. Like instead of having the massive open pit mining that we know, going underground is when it's possible is one way to reduce the amount of material that you can extract out. So in our scenario, we also considered how much underground mining could be done as well. But to answer your question, yeah, it's not easy. Clearly, all of these approaches have some sort of costs. So there are ways. So when you we use reprocessing, there are ways to extract more metals and recover some of the value while at the same time investing in environmental desulfurization. So an incentive can be that, okay, there is a requirement to rehabilitate and to make the rehabilitation of the site economical. We can recover some metals on the site as well as a way to finance the rehabilitation of the site. I think what we say at the end of the paper is to say that, okay, there are new societal demands. Local communities may not accept the type of mining disturbance that happens still today, especially if some mining is going to happen in Europe. Maybe societal demands just won't allow for the type of disturbance that has been allowed to happen in the past. So we are also hoping that this will be an incentive for mines to consider alternatives to the business as usual.
Lovely. Thanks, Eleanor. Thanks for that. I think a similar kind of question, Stefan, to yourself is, it's a fascinating way of looking of this kind of deferred impact of, high levels of consumption in the global north, high demand, but a lot of those resources are coming from the global south, who are kind of left with this environmental impact and the legacy of mining. And it's so interesting to see that the big impactors of deforestation were gold and coal. As we see the energy systems transition towards renewables, there's a change in the types of materials that are needed, greater demand for rare earths. Can the modeling work that you've done be used almost to kind of predict where we're likely to see future deforestation and future impact, that we can actually start to manage those risks now ahead of the time, and some way, again, talking about drivers, some way build that risk of deforestation into that demand to kind of force and to change practices?
Mm-hmm. Yeah, thank you, Linda. Also very good question. So far, our research has focused basically to set up a methodology for the historical development or the current system. What we are working right now is to do a first estimation of the current, say, deforestation intensities per commodity, which would then allow to at least provide a rough estimation if under given intensities of deforestation, the extraction of, say, nickel or other metals needed for the energy transition would increase, what would be the effects on deforestation. But yeah, we are also working with other groups more specialized on the question, where can we expect future mining? And what I learned from them is that it's also quite difficult to predict where future mines could open, because this has also geological opportunities and then questions involved, which determine cost structures, and then legal aspects come into the play. So there's a lot of research going on right at the moment. Also, I know with Australian groups who try to establish models that better predict where we can expect future mining to expand. And then based on that, maybe with our knowledge on the historic trends of deforestation impacts per commodity, we could then link this to provide an estimation. But there is certainly a way to go, basically, to reduce the uncertainties in those types of assessments.
Thanks, Stefan. Thank you. We've reached the end of our 45-minute time slot for our first session of this morning. So I'd like to give a very big thank you, Eleanor, Stefan, Gerfried. Thank you for your presentations this morning. I think that people do have your contact details who are joining us online. So again, if there are any questions that they have, feel free to engage through the app with our speakers this morning. I have some additional questions I'd like to follow up on as well with you post the session. So a very big thank you for your excellent presentations this morning. And again, for those who are joining us online, a reminder to please vote for your favorite or best presentation from this morning. So thank you to our three speakers from our first slot. With that, then, I would like to move to our second slot for this morning. And our first speaker, and I just want to make sure that Mei Ling has joined us. Our first speaker for this morning is Mei Ling Loko from Yale University and Willow Technologies in Ghana, who will be talking about Ghana and Senegal's residential boom, opportunities for scaling local biogenic and geogenic building material resources. I'm certainly intrigued to see with a title like that what the presentation will be about. So Mei Ling, let me pass it directly over to you. You should hopefully have control of the slides, and I look forward to your presentation.
Thank you, Linda, and thank you, everyone. There's a slight delay, I believe, with the screen, but just an introduction to the presentation. This is sort of a global study funded by the United Nations Environment Program, linking directly the impacts of building material sectors on climate. And so we're focusing on a life cycle assessment of building materials in the major building materials in Ghana and Senegal. And I'm representing a much wider team on the ground through Ghana's CSIR and a number of research firms based in Dakar and Senegal. So over the course of this century, the largest increase in population growth will be on the African continent. Over 75% of global population will take place in the sub-Saharan African region, and the rising demands to provide housing for 3 times its current population means that there's going to be incredible pressures to drive land use changes, which may threaten to invert this region's role from being a global carbon sink, important carbon sinks in this region, into a carbon emitter. To date, while the region has contributed only 2% of global carbon emissions, which represent the lowest emissions per capita, it has been acknowledged as one of the most environmentally and economically vulnerable regions to climate change. Projected housing needs really are going to grow now in the coming era, the rest of the 21st century. Our study really looked at some of the key shifts that are happening in the building material sector. Ghana and Senegal were chosen due to its economic and its urban growth rates, which are between 4 to 5%. They're mid-sized, or the capital cities are mid-sized cities, but represents some of the patterns we're seeing around growing housing deficits, which in Senegal are about on the order of 300,000, and in Ghana as much as 1.8 million per year. Taken together, we started looking at a life cycle at the embodied and operational phase. One of the biggest patterns we're seeing is that the building materials sectors in both countries are entrenched in high carbon development pathways. Over 80% of building materials are imported, and 80 to 90% of all housing in Senegal and Ghana remains self-built. These are bottom-up models of construction. Concrete masonry, in particular, represents an overwhelming percentage of wall construction, as high as 82% of all homes in Ghana and 70% in Senegal. And we're seeing the replacement of a lot of roofing building materials with metal sheets, as high as 80% in Ghana, and concrete masonry in Senegal to the tune of 71%. Across both contexts, there's also an increasing dependency in the lifetime of the building on the shift to modern energy surfaces, which rely largely on petrochemical energy sources. There's sort of a huge shift from hydroelectric to sort of natural gas in the last decade. Sorry, I think there's a delay with the slides. Okay. And one of the biggest, sorry, can I go back? One of the biggest opportunities to decarbonize, can we go back one slide? Thank you. Okay. Okay. One of the biggest opportunity is to really look at alternative low carbon local material streams in the form of agricultural waste and invasive species. One of the biggest agricultural wastes growing in the nation, which is part of a byproduct of a coconut water and coconut sort of oil industry, are the generation of husks, coconut husks, which are typically burnt in open air in cities or prematurely downcycled back as fertilizers or soil substitutes in agriculture. In Ghana, the coconuts can be upcycled into pressed medium density fiberboards to high density fiberboards, which are capable of replacing plywood and taking the pressure off West African forests. In Senegal, the growth of invasive species like Tifa reeds in the Senegalese rivers offer a really interesting fiber additive to earth masonry technologies. Earth-based masonry has had a long-standing history in West Africa, and due to the rise of pollution and the growth of these invasive reeds, a range of products ranging from insulation to roof slabs to biocomposite earth, sort of Tifa clay composites, promise a range of advantages, including lower embodied carbon and a range of improvements over the lifetime of the building. Due to their high porosity, they have great hygrothermal performance, which can lower indoor humidity and temperature patterns throughout the building. And at the end of their life cycle, offer other ways of degrading into the environment without a lot of toxicity. So looking at the major residential typologies, our teams on the ground identified through census and national studies, the major housing typologies, where we studied all of the building materials found in representative buildings. One of the biggest findings is that no housing typology is created equal. The Ghanaian detached, the single house family typology has the highest carbon footprint, close to 1,500 kilograms of carbon dioxide equivalent per person per year. And we can also see in yellow in this chart on the left, the high carbon emissions in the operational phase, in the use phase of the building. And this is not just a function of HVAC systems, but it's also exacerbated by the design and integration of high carbon building materials like the hot roofs and the concrete masonry sort of walls. And so one of the biggest findings from the study is the impact of integrating some of these biogenic and geogenic materials in the building envelope, which we'll see. Sorry, I think there's a delay in the slide. Great. Across sort of equatorial territories like Ghana and Senegal, where a majority of the building heat gain is actually mediated by the roof, the impact of insulation under metallic sheathing has by and large the hugest impacts. And so we can see on an order of sort of 4 to 5 per, 60% we're seeing drops in detached and compound housing typologies, these sort of low rise typologies, the drop in carbon dioxide emissions, operational carbon, particularly in the use phase. We also see in the Senegalese housing typologies, due to the fact that the climate is sort of hot, arid, the use, albeit slightly less, is achieved by using Tifa fiber masonry roof systems relative to methyl sheathing. There are also other huge outputs from the the study, which will be published in the report that is coming out in Climate. This was the big takeaway. I just wanted to also go over some, as a conclusion, some other opportunities for using some of these biogenic and geogenic resources, which might be for cement producing countries like Senegal, the substitution of sort of petroleum or sources with biomass agricultural waste in the production of large building material sectors like cement. We can also see them input it as supplementary cementitious materials, which improve the mechanical performance and really reduce the role of cement in concrete masonry systems. For countries like Ghana, where we largely import cement and a lot of the timber is exported to Europe and other parts of the world, the advantages of using some of this biomass to replace plywood and provide construction, particularly for informal contexts that use a lot of these materials, is massive. These typically have lower embodied carbon simply because their adhesives and binders are typically use half the amount of temperatures and pressures that we see in plywood industry. And being the fact that they are agricultural waste, there is zero burden material, entering the system boundary. And so I'll end there and look forward to questions. Thank you.
Thank you very much, Mei-Ling. Again, I don't see any questions of clarification in the Q&A. Just a reminder to those that are joining us, online conference attendees, please feel free to pop your questions into the Q&A, and also if you're joining on the app, I'm hoping that our tech support may be transferring some of the questions over to us here in Zoom. So with that, let me then pass over to our next speaker for this morning, Christos Achilles from the International Hellenic University in Greece. The title of the presentation is Real-Time Sensor-Based Assessment of Environmental Impacts in Industrial Production. Christos, over to you.
Okay, thank you, Linda. Let me check that I can control the screen. Yeah, okay. All right. Okay, thanks a lot. Thanks for the kind introduction. I'm Haris Achilles. I'm Christos Achilles. I'm an associate professor at the International Hellenic University in Thessaloniki, Greece. But apart from this affiliation, I have also another hat, being a partner in Engineers for Business, which is a startup that is focused in building ICT solutions, mostly focused on environmental engineering. So the work that we will present you today is coming from one of a research project that is funded under Horizon 2020 program, Kyklos 4.0. And at this moment, I will give the floor to my colleague, Nassos Kalaitsidis, who is mechanical engineering. He's an LCA expert, and he is the one who is very actively involved in this Kyklos 4.0 project. So, Nassos, the floor is yours to present what we have prepared in the development of LCA engine.
Thank you very much, Haris. So yeah, I also work at EFP, where we are a company already 9 years alive, doing research and environmental studies and programs. And we have developed through the Kyklos 4, which is a Horizon Europe project, we have developed a software that helps people to create dynamic LCA, which means the dynamic is, we gave the definition of dynamic that it can take sensors, it can take live data from a factory, which could be our client, for example, and giving real-time data to cradle to grave or cradle to gate analysis to the product, so that they can change their properties, they can change their amounts of resources using, or just their electricity and water. So that's the need that we found, that there's a lot of there's a big market in Greece and also in Europe, and the rest of the world, for example, that they need this dynamic, this connection of the sensors to the number, to the score of their impact of their products. Sorry, the slide. So yeah, at the right side, you can see the dashboard. You can see that it's a web app, which also can be used on the mobile. And for now, it uses some databases, for example, EcoInvent, and it is compatible with some ISO, so our clients can create some reports to be certified with those ISO that are for EPDs, for example, or the greenhouse gases ISO. But the most important part of this presentation and our product is our real-time functionality, which enables people to combine their situation in their factory, for example, if we are speaking about the production line, and create this dynamic, this real-time number, this amount of numbers that they use to create, to take decisions, or to give to modify their policy, for example, according to what they're using, their resources, the ways they produce. It also has a very useful, like a very light user interface for people to really create. Let's say it's a rapid prototyping to the LCA side, though. And it has a real flexibility as a software, which means that it can very easily communicate with other machines through APIs, which are developed, and it's an ongoing process. This is actually a beta version. I had to say that this is a beta version of the software. We are having some pilots and some tests using to this, and we are always developing and creating, expanding our team. Here you can see that the software gives you a graph of the last 50 numbers, 50 data that it had received from the sensors. Although you can do a lot of modifications and configurations. We will see a demonstration video later. So that's a scheme. That's a rough scheme of what we are doing. Where's our part? So that's, for example, our client or our calculations for our tests. Here we create a digital twin in our software, which can be integrated with the LCI using Nexus, databases or other commercial databases, and result to the LCA results. But it is dynamic, so that if we change through sensors, if we change the use of water, for example, or electricity, we can see the impact immediately through using this software. And here is a demonstration video, which is like you can see how easily interface. That's the dark mode. Here we can see the production used in the end of life, which can also be named as upstream, core, and downstream, which are the parts that are happening inside the production line, inside the factory on the industry. We create a process, and then we add the flows, for example, electricity, water, chemicals, or it can be also embedded. So we can use like tractor if we're talking for agricultural activities, or we can use whole buildings, whole embedded impact of the buildings through the WRF23 or any other version of it. So that's the process that we link to the sensors. It's from a specific client of ours. It's a pilot inside the Kiklos 4 project. And here at the end, you can see the graphs and export the numbers to use them. So yeah, the exporting can be on JSON, XML, and Excel formats. So thank you very much. Thank you very much for your attention. Me and Mr. Harris are finished with our presentation.
Wonderful. Thank you very much, Chrysios and Assos. Let me just see. Again, I don't see any Q&A questions, so I know I've got some. I'll circle back to those as well. But thank you very much for your presentation, and let us move on to our final speaker for this morning's session, Vladimir Gedmansky from Alex in Ukraine. The title of the presentation is Empowering Sustainable Buildings, Data-Driven Solutions for Estimating Energy Needs and CO2 Emissions. Vladimir, over to yourself.
Yeah, thank you. Okay. Yeah, so thank you for the organizer committee for organizing such conference. My today's topic is about the energy needs estimation, the same as the carbon footprint estimation. My name is Vladimir Gedmansky. I'm head of data science office in Alex. Yeah, and previously we have started a set of different initiatives in the sustainability service, and here is one of our latest research about that estimation of the energy needs and carbon dioxide footprint. Yeah, the first slide here is about well-known information about the life cycle stages that you have heard from the previous presentations. And there are at least 4 huge existing approaches on how to estimate the possible energy need for different stages of this LCA, and how to evaluate the possible or pessimistic and optimistic carbon footprint. The first is the GLEC framework. It is the framework typically used for the logistics activities, but here, as we can see in the scope of the LCA parts, there is construction processes and offline processes where the logistics of materials of different layers of the building are very important. The second possible approach is the scope estimation, where the scope 1 is the pretty closest to the construction company any emissions or energy needs, and for example and the opposite, the third scope, are the most far from the company activities and typically related to the suppliers' activities or users' activities. The third one is the buildings information modeling. So you also have seen some partially from the previous presentations, and this model uses the decomposition of the building to different layers and then estimating based on the U values or other features, estimating the possible energy need for the heating or for other activities, the same as related carbon footprint. And the first one is the simple additive models. You can see the example below, where we can simply multiply different resources, distances, or other values like power, like time of activity, calculate per some standard or per some coefficient, like, I don't know, gram per kilometer, and then estimate some average values for some specific activity. There are some obvious cons of all of these methods, just because for some of them we can use only some average values, just in advance known norms or standards or such coefficients to calculate the final footprint or calculate the final energy needs. But exactly, they can be different for different style of usage or for different pattern. The same, another cons is then when we want to evaluate or measure something very precisely, we need to use many measuring devices or even huge IoT environment or network that is hard to be scaled. For example, setup for one building with known IoT can't be extrapolated to the huge region, for example, for 1,000 buildings or something like that. Also, returning back to the our scope of the life cycle assessment, we can see that the usage stage or the operational stage takes over 85% of the total carbon emissions, the same as energy needs for the operational activities. That's why we try to focus mostly on the usage stage of this LCR cycle. Yeah. And try to use approaches from the classical machine learning that can help to extrapolate known sensitivity or elasticity of our features to all other buildings in that region or in others. And finally, to estimate the emissions or estimate the energy need for huge regions. Okay, we took several attempts to get the data from any like scientific organization or any government organization, but finally found the public sources, that the source that we show on this slide, where there are different features of our buildings, the same as used in the buildings informational modeling, where the building is decomposed to some parts. And also from that data, we can take the year of construction or other features, the same as our objectives. Here you can see the feature, our feature list that consists of the country, that can give additional information about the climate zone, about the building size, about the year of construction, different features related to the surfaces, to the materials, the same as to efficiency of these materials called U values. And finally, there are like two our targets. The first is the energy need, and the second one is the emissions. Based on these features, we have provided some simple descriptive analysis, and we may see that most of our buildings are from the Ireland, from Greece, from Italy, but also from other countries that can cover or generalize the information about the climate coverage. Also, we have different building size classes. And talking about the further modeling, there is no multicollinearity in our features that we can see from our correlational matrix. The same, there is no huge linear correlation between our features, any of our features, and the energy and emissions that are our objectives. That can also show us that it is not the easiest task to be resolved. Here we specified several typical estimators from the classical machine learning without any deep learning, just because it is like the first try. And firstly, we should validate the proven methods. And you may see that for all of our targets for energy need and carbon dioxide emissions, the average percentage error goes from the 20% and up to 30%. Based on these plots that are shown below, we may see that the behavior of the errors are probably closer to some homoscedasticity, and only there are like several cases or samples where the deviation from the average error is larger than expected. And the most efficient models to resolving this task are the ensemble models, like boosting models, where we have used 200 of trees with the depths of 10 splits. Yeah, and you can see the additional statistic provided on these graphs. After building such estimators, it is possible to provide the factor analysis, starting from the feature importances for both of our objectives. And you may see that the country, probably as a climate type, the ventilation system, or the materials features have largest feature importance for our predictions. And finally, there is additional factor analysis called the Shapley values analysis, where the game theory used. So each sample here can be treated as a player in the game that can affect the final objective in different ways. You can also see that the U values has the largest influence, but also some of the U values, for example, for door U value or wall U value, for energy need and carbon dioxide emission, also have some deviant behavior. It can be so due to the final representatives of our sample, just because it is hard to say that it is general sample. And finally, I think we should have additional data gathered from different countries and representing different types of the buildings. Okay, then goes the conclusion. So firstly, yeah, we have provided the typical machine learning approaches for covering these tasks that are typically measured by different methods. And that method, that classical and known methods, have its own cons, like starting from the using the average standards or average coefficients for different activities. That is quite inaccurate. The same as using the very precise measurement with the measuring devices with the IoT infrastructure that is hard to be scaled. Our method, or typical machine learning method, shows here that it can be used for estimating such energy need and further carbon footprint for larger regions where we can get the information about each building. There is no high correlation between our independent variables. That is quite good. And among the factors, we can face the logical influence of that feature that typically is used for such estimation. That's why we may say that this approach is adequate, has its own adequacy to the modern approaches. Yeah, as I said, it is only one of our current initiative, which we have provided within our sustainability service. Yeah, nowadays we have our also attendee in the poster section, Любомир Мацех-Український, who can explain a little bit more about all others activities in our sustainability service. So you may contact him in case if any additional questions about the general map of the sustainability can appear. Well, that's all from my side. So thank you for your attention, and probably there are some additional questions.
Wonderful. Thank you very much, Vladimir.
Yeah,
that brings us to the end of our 3 presentations from slot 2 today, and opportunity for some questions and discussions for this final session. A very big thank you to our 3 speakers, Mei-Ling, Chrysios, Nasos, and Vladimir. I'm going to jump in first because I am chairing, and so I have the ability to ask questions before the one that has been posed in the chat box, if I may. And Mei-Ling, it's to yourself. I think, you know, one of the things that it kind of continuously on my mind is that, you know, this issue around population development, urbanization, a growing middle class on the African continent, is we are going to see a lot of stress on our built environment moving forward, and a lot of demand in terms of improved housing, buildings, infrastructure, etc. But I also do believe that, you know, the pandemic disrupted the way that we live and we work. And I honestly believe that there's an opportunity for Africa to invent a future for itself in terms of its built environment that could look very different to the development path taken by the global north. And so my question is, should we be continuing along this journey of urban sprawl, single-family homes, and just looking for different types of building material like biogenic or geogenic materials? Or is there an opportunity to rethink how we actually build the cities of the future in Africa that integrate, the work and the play environment into the way that we live, and create more densification? Because the problem with urban sprawl, and if we're going to accommodate, I've seen the figures for Nigeria, for example, in terms of population growth, the urban sprawl would be so significant with single family homes that we would just fail in terms of wastewater, water supply, solid waste collection, the road infrastructure, energy systems, etc. So I'd love to get your thought in terms of, how do we shift the conversation away from what materials do we use to rather what are we actually building in Africa to create a more sustainable built environment? Thank you.
Absolutely. Yeah, no, that's a big question. And one of the key things we're learning from this study is what you saw on that chart, that the single detached family home is not a good model, carbon-wise, land grab use-wise, energy-wise. Typically these houses, lead the way, and energy and roads follow them. And so I think that there's, a number of ways of answering that. One is, the way in which we densify is really important. So for example, for providing energy, there's a real opportunity here to really match the kind of supply of energy, renewable and non-energy, and the types of programs, whether it's industrial and housing, right next to each other. And one of the most interesting examples we saw is what is happening in the DRC with metro grids, where you have, sort of a non-renewable, reliable resource. It might be fossil fuel, it might be geothermal, paired with, more variable energy resources like, solar and wind. And because industry is situated right next to residential programs, particularly those that they can subsidize, then there is a sharing of energy in that sort of housing and industrial complex. And this is dense housing. And in the study we did take, although I didn't show, we took two really interesting examples of low density and high density residential vertical dwellings that are built on the compound typologies that have been sustaining the urban populations for a long time in both Dakar and Accra and other major cities. And so what was really interesting to see is low density, more upper middle income, vertical compound typologies were the most energy intensive sort of housing typologies over its lifetime carbon emissions relative to the high density. And so that's some case studies in this report are key for showing the other types of lifestyle and occupation and health, and well-being opportunities that might exist in these types of buildings. So it's a big question. I do think in the biggest gain is really rethinking our energy and our lifestyle, and building materials, and new modes of sort of living and sharing is sort of emerging within that sort of nexus.
Thanks very much. Yeah, I think, I wish we'd have kind of that visionary leadership on the continent that really forces us to rethink our development path. And also, just given the levels of energy insecurity, water insecurity, I think there's an opportunity to address all of these big societal challenges just by rethinking the way that we actually develop our built environment moving forward. Thank you for that. All right, we've got a question, Karisios Nassos, for yourself, and I think this probably also extends to some degree to yourself, Vladimir, because it speaks very much to this issue around data and LCA, which can, that data, garbage in, garbage out. We sometimes rely on data, and there's always a danger to it. It makes me sometimes a little nervous around LCAs. But the question that we have, first of all, Karisios, to yourself, which production sectors can you cover well with your tool? And are there significant data gaps in some sectors, or is LCA data availability and quality sufficient across all production sectors?
Well, we have tested our tool in several sectors within the project. Nasus, you can name them.
Yeah, it's on the food industry, on the automotive, on service providers. Yeah.
Also in agriculture business.
Yeah, in agriculture. Yeah. So the limitations of the sectors, it's on the databases. If we integrate the database that covers the sector, then we have the sector. The most interesting part actually is that the gaps of their production lines, because from our side we don't create any new data, any databases. But the industries don't really have the industry 4 adapted to their constructions. For example, the agriculture in Greece, like they have a very old fleet of tractors, so it's very difficult to take some data from there. Although many of the industries in Greece have incorporated some modern ISO certified production lines that have total control of their amounts they're using, of their numbers, so we can aggregate them and then cover this gap of data. But it's a small amount, at least in Greece and in Europe.
If I may add about the agricultural sector that Nasus mentioned, we are connecting our tool, our LCA engine, with a farm management information system, FarmD, which is, this system collects all the data we need, and we try to adjust what we need from such an information system in order to provide valuable information because, we can provide massive data, but the thing is that you have to analyze it to know what is interesting for your client. And this is what we are working at the moment now.
Yeah, and this application actually covers some of the data that are missing from the fleet or from the agriculture. This application, FarmB, covers some of these parts.
Thank you. Vladimir, would you like to comment on that as well in terms of data? Because I noticed that you did comment in your presentation around the need for country-specific data, etc.
Yeah, so as I said, it was hard for us to gather or get any data from the government or even scientific organization about this study. Also, as I said, there are like different methods. Some of them require some average values, like power usage of vehicles, like distances or time. That can be some observation from your like construction stage or something like this. But typically, there is no efficient data for the huge like time for large time duration of the operational usage of the building. So it requires some even years to gather this data. That's why the only resource we found that I shared with you, and it consists of some values for some limited amount of buildings in limited amount of countries. In case if it can be extended by any like other organization, a governmental organization, it will be very helpful for the machine learning approach. Just because, as I said, it is not the end of life or constructional phase where you can calculate some known amount of vehicles per some time of their work or something like this. It is of the of different people usage, how they use the energy, what are the materials for their build, just because any building is unique and there is no possible way without the IoT to measure or to estimate it. Yeah. That's why, yeah, the data sets are quite important here and even more important than for other LCA phases. And there is no any like well-known and unique database for it.
And I think certainly, based on my experiences, perhaps if you within the EU member states, maybe USA, Canada, developed countries, the data sets are probably quite intense and quite relevant. You know, the data is collected from those regions, but as one starts to move, for example, into Africa, South America, maybe Eastern Europe, for example, sometimes we find those data sets are just not relevant. Our energy systems are different, perhaps more carbon intensive, for example, or, forestry, if you're talking about, using wood in built environment, just the nature of forestry is quite different. And so it was quite a challenge in terms of finding relevant data sets, from the likes of EcoInvent, etc. So it really is important to make sure that we're getting reliable data from the global south into these big databases as well to help to inform the LCAs that are conducted. Thanks, Vladimir. I see you've popped the link there into the chat box with regards to the data set used. So that brings us to the end, 12:30. It seems that we've flown through this, and I've still got so many questions I'd love to ask all of you, but unfortunately we've run out of time. So a very big thank you to our presenters this morning, Carisios, Nassos, yourself, to Mei Ling, to Vladimir. Thank you for the excellent presentations, and to everyone who is joining us online this morning, please do remember to vote for your favorite presentation from this morning. And with that, again, to the presenters from our first session and to our second session now, a very big thank you from myself and from the conference organizers for the excellent presentations and for the engagement this morning. Thank you.